In early 2011, along the coast of Ishikawa in Japan, a fisherman comes across something lying half buried in the sand. At first, it does not look real. A long silver body, reflective and ribbon-like, with a red crest running from head to tail. It is longer than his boat, and it is still moving, slowly, barely. He does not call the Coast Guard, he calls a priest. In this part of the world, the animal already has a name. Ryugu no Tsukai, the messenger from the palace of the sea god, and the message it is believed to carry is always the same: something is coming. This is not an ordinary fish, it is the longest bony fish alive on Earth. Some verified individuals have reached lengths of more than 17 meters, and almost no one has ever seen one alive where it actually lives, because it does not belong near the surface. It lives hundreds of meters down, in a part of the ocean where light fades out and pressure builds to levels the human body cannot survive. And yet, at certain moments, it appears, not one, but several. In the weeks following that first sighting, more of them begin to surface along the same coastline. By the time it stops, nearly 20 have been found. Then, on March 11th at 2:46 in the afternoon, the seafloor shifts. The earthquake that follows is the most powerful ever recorded in Japan. The tsunami reaches over 40 meters in height, and nearly 16,000 people are killed. That alone would be enough to turn this into a story. But it does not end there. Similar appearances have been reported before other earthquakes, different locations, different years, the same animal appearing just before something breaks. Scientists have tried to test this. Hundreds of deep-sea fish strandings compared against major seismic events. The results do not confirm the connection, but they do not remove it either, which leaves a gap. Because for this pattern to mean anything, the fish would need to be detecting something before it happens, something deep, something physical, something we are not directly observing, and that is where this story moves next. Today we follow the evidence behind these appearances, what this animal actually is, where it lives, and what might be happening beneath the surface when it rises. But before we do, let me know in the comments if you have any topic suggestions you would like me to cover in future videos. Now relax, and let's begin. Long before it was given a place in scientific language, this animal existed as a shape, glimpsed only in fragments, a length of silver drawn briefly into the human world, before vanishing again. When it was finally described in formal taxonomy, it received the name Regalecus glesnae, placed within a family whose title carries the meaning of something royal, a quiet acknowledgement of its scale and presence in a realm rarely seen. It has been called many things across different waters: ribbonfish, streamerfish, king of herrings, each name an attempt to translate a form that resists easy comparison. Its body does not resemble the familiar structure of most fish. It is long and narrow, laterally compressed into a thin ribbon-like profile that can extend to extraordinary lengths. While many individuals measure closer to 3 meters, verified specimens have reached up to 17 meters, making it the longest bony fish known to exist. Despite this immense size, its weight remains relatively modest, sometimes approaching 270 kilograms, a result of a body composed with minimal muscle and an almost delicate internal structure. The surface of the oarfish reflects light in a way that feels almost unnatural. Instead of traditional scales, its skin is coated in a layer of guanine crystals, creating a silvery mirror-like sheen that shifts subtly with movement. This reflective surface catches what little light filters down from above, scattering it into faint glimmers that ripple along its length. Running from the top of its head and continuing uninterrupted to the end of its body is a vivid dorsal crest, composed of hundreds of fine rays that form a continuous flowing structure. Near the head, these rays lengthen into a striking red crown, a feature that has lingered in human memory far longer than any scientific description. Its mouth is small, almost understated, lacking teeth entirely. It extends forward when feeding, drawing in water and whatever small organisms drift within it. Plankton, tiny crustaceans, and small squid form the entirety of its diet, consumed through a method that depends on patience rather than pursuit. There is no forceful chase, no sudden burst of speed, only a quiet filtering of the surrounding water. Movement itself follows a pattern, unlike most fish. The body remains nearly rigid, held straight as a narrow line, while the dorsal fin undulates in a continuous wave from head to tail. This motion, known as ameiform locomotion, allows it to glide forward with minimal disturbance, conserving energy in an environment where resources are sparse. At times, it abandons the horizontal entirely, drifting into a vertical posture with its head angled upward and its tail pointing down into the deeper dark. In this orientation, it becomes less a swimmer and more a suspended line within the water, its full length exposed to the subtle gradients of pressure and motion around it. Unlike many marine species, it shows no evidence of traveling in groups. It exists alone, moving through vast distances without companions, crossing temperate and tropical oceans across the planet. Its presence is not tied to a single coastline or region, but to a depth and a condition that exists everywhere beneath the surface. There is no commercial interest in the oarfish. Its flesh, gelatinous and fragile, offers little value as food. It is not hunted, not cultivated, and not deliberately sought. Most encounters occur only when something has already shifted, when the boundaries that usually hold it in place have loosened. In its natural state, it remains almost entirely unseen, a long, reflective body suspended in a world defined by stillness. Everything about it suggests an existence shaped by restraint, by quiet movement and minimal resistance, by a balance maintained without effort. It is not built for speed or struggle, but for endurance within a narrow set of conditions that for the most part remain undisturbed. Far below the restless surface, there is a layer of ocean that exists in a state of gradual fading, where light does not disappear all at once, but withdraws slowly, as if reluctant to leave. This region is known as the mesopelagic zone, a band stretching from roughly 200 to 1,000 meters beneath the waves, often described as the twilight zone, though even that name feels brighter than the place itself. Here the last traces of daylight dissolve into a dim blue haze, thinning with depth, until it becomes something closer to memory than illumination. At its upper boundary, a faint glow still lingers, soft and diffuse, enough to outline movement but not to define it. By the time the depth reaches 500 meters, even that glow has nearly vanished, leaving only a muted gradient that slips into darkness. Beyond this point, the ocean no longer reflects the sun in any meaningful way. Vision becomes secondary to other senses, and presence is felt more through pressure and vibration than through sight. The weight of the water increases steadily with every descent. At the lower reaches of this zone, pressure rises to nearly 100 times what exists at the surface, compressing everything into a state of quiet tension. Temperature follows its own slow decline, settling between 4 and 8 degrees Celsius, hovering just above freezing. The water here is cold, stable, and remarkably still. Unlike the upper ocean, where currents shift and churn, this layer holds a kind of suspended calm, a vast body of water that moves so gently it can feel almost motionless. Within this stillness, the structure of life adapts accordingly. The oarfish carries almost no muscle because it does not need to fight against resistance. Movement requires little force, only continuity. Energy is conserved, not spent. The environment favors organisms that can endure rather than pursue, that can remain poised within the water rather than push through it. When that balance is disrupted, the consequences are immediate. If an oarfish is carried upward into shallower water, it enters a world defined by motion. Waves introduce constant turbulence, currents shift unpredictably, and the once stable environment becomes chaotic. Its body, built for stillness, cannot accommodate this change. The gentle undulation that once sustained it becomes ineffective, and the physical strain begins almost at once. Surrounding this narrow band of depth is a community of life shaped by the same constraints. Many species here generate their own light, producing soft glows that pulse or flicker in the darkness. Others are nearly transparent, their bodies designed to vanish against the faint residual light filtering from above. Some possess eyes of unusual size, wide structures capable of capturing the smallest traces of illumination. Each adaptation reflects a negotiation with an environment where energy is limited and visibility is uncertain. The oarfish itself has been observed to emit a faint bioluminescent glow, subtle and not yet fully understood. It is not a bright signal, but a quiet presence, as though its body carries a dim reflection of the world around it. Nearby relatives, such as the streamerfish, have demonstrated the ability to produce mild electrical discharges, suggesting that this lineage may interact with its surroundings in ways that extend beyond simple movement and feeding. Despite its scale, this environment remains largely unexplored. Scientific observation has reached only a small fraction of this zone, leaving vast areas unrecorded and unmeasured. The difficulty lies not only in the depth, but in the conditions themselves, where pressure, darkness, and distance limit the duration and scope of exploration. Much of what exists here is known only through brief encounters, fragments collected and interpreted without the full context of their origin. Beneath this layer, the seafloor forms a boundary that is anything but still. In many regions of the Pacific, it lies directly above active fault systems, where tectonic plates shift slowly against one another, building and releasing tension over time. The water above may appear calm, but far below, the Earth itself is in motion, shaping the conditions of the world above it in ways that are rarely seen, but always present. There is a long stretch of time in which this animal existed without ever being properly seen, not in the way science prefers to see, alive, undisturbed, moving through its own environment. Knowledge gathered during that period formed slowly and unevenly, assembled from fragments that arrived only after the original context had already been lost. The first clear record of a living individual in its natural depth did not appear until 2001, when a remotely operated system captured its presence in passing, a brief encounter framed by machinery rather than direct observation. Several years later, in 2008, another recording showed one moving through open water, its length estimated between 5 and 10 meters, its motion steady and deliberate. Yet even this moment felt more like a glimpse than a study. Before those recordings, nearly everything known had come from bodies found at the surface. These specimens were not representatives of normal behavior, but the result of disruption. When an oarfish rises into shallow water, it does so under conditions that are already abnormal, driven upward by forces that have unsettled the balance it depends on. Injury, internal imbalance, or disorientation may all play a role, but the change in pressure alone is enough to alter its physiology in profound ways. As it ascends, gases dissolved within its tissues expand, distorting internal structures and interfering with basic function, a process comparable to the effects experienced by divers when ascent is too rapid, though here it occurs throughout the entire body. By the time it reaches the surface, The outcome is rarely uncertain. Most individuals survive only a short time after arrival, their systems unable to adjust to the new environment. Even attempts to assist often accelerate decline. The skin, so finely adapted to its original conditions, reacts poorly to contact, breaking down almost immediately when handled. Exposure to air and light begins a process of deterioration that moves quickly, leaving only partial evidence of what once existed intact below. Attempts to keep an oarfish alive in controlled conditions have never succeeded. The transition from its native environment to any artificial setting introduces variables that cannot be fully compensated for: pressure, temperature, and the subtle qualities of deep water that remain difficult to reproduce. Without those conditions, stability cannot be maintained. Each attempt has ended the same way, reinforcing the limits of current understanding. The absence of direct observation extends beyond simple behavior. There are no confirmed records of mating, no documented spawning grounds, no clear timeline for growth or aging. Even lifespan remains uncertain, inferred only through indirect comparisons with related species. Population size is similarly unclear, as encounters are too infrequent and too scattered to support reliable estimation. What appears in records may represent only a fraction of what exists, or it may reflect a population that moves through vast spaces with little overlap in observation. As a result, much of what is believed about the oarfish rests on interpretation rather than direct evidence. Bodies recovered from shorelines provide structure, measurements, and certain internal details, but they do not preserve the conditions that shape them. Decomposition begins quickly, altering features and obscuring finer characteristics. The living animal, with its full range of movement and interaction, remains largely beyond reach. In this way, understanding develops in reverse, starting with the end point and working backward toward an origin that has yet to be fully observed. Each fragment adds to a broader outline, but the interior remains incomplete, defined as much by absence as by presence. The oarfish continues to exist within that gap, a species known in form yet still distant in function, its life unfolding mostly outside the boundaries of what can currently be witnessed. Accounts from open water have always carried a certain distance from certainty, shaped by the limits of what could be seen, remembered, and retold. Long before instruments extended human perception, sailors described encounters with forms that did not align with any known creature, elongated bodies moving just beneath the surface, rising and disappearing with a motion that felt unfamiliar. These descriptions appeared across centuries, often recorded with care, yet framed by a sense that what had been witnessed could not be easily explained. Many of these reports shared striking similarities. The bodies were described as exceptionally long, sometimes exceeding 30 meters, their forms narrow and continuous, with a reflective quality that caught light in shifting patterns. Along the upper edge, witnesses noted a crest or mane, often red in color, trailing through the water in a way that gave the impression of movement, even when the body itself remained still. These details found their way into the mythologies of distant cultures, shaping images of sea serpents in regions that had no contact with one another. In the northern Atlantic, the Hafgufa was described as a creature so vast it could be mistaken for land, its presence revealed only when the water around it shifted. Far to the east, traditions spoke of a dragon associated with the sea, an entity tied not only to tides, but to the deeper movements beneath them. These narratives, though separated by geography and language, shared a visual consistency that suggests a common origin rooted in observation rather than invention. When examined alongside known biology, a connection begins to take shape. An oarfish at the surface does not move like other fish. Its propulsion comes from a wave that travels along its dorsal fin, leaving the rest of the body largely rigid. From a distance, this produces a motion that appears sinuous and continuous, a single line bending and unbending in slow rhythm. For observers unfamiliar with such movement, especially from the unstable vantage point of a small vessel, the impression would be unlike anything previously encountered. The crest, vivid and elongated near the head, reinforces this image. In calm water, it rises above the surface in thin, flexible strands, catching light and shifting with even the slightest motion. Across multiple accounts, this detail appears with remarkable consistency, described as a mane, a ridge, or a line of color running along the creature's length. The repetition of this feature across independent traditions suggests that it was not imagined but observed, then interpreted through the lens of existing belief. There is another layer to consider, one that emerges after the creature has died. As decomposition begins, the more delicate structures are lost first. Fins deteriorate, soft tissues break down, and the body begins to change shape. What remains is often a long, pale form, lacking the features that would clearly identify it as a fish, washed ashore or encountered floating. Such a body could easily be mistaken for something entirely different, especially in an era without comparative reference. Photographic records from the early 20th century include several examples of so-called sea monsters that were later re-examined with greater scrutiny. In multiple cases, the underlying structure aligned with that of an oarfish in an advanced state of decomposition, its defining characteristics no longer intact. One notable instance occurred in the early 19th century along the coast of Scotland, where a large carcass was described as a creature of great length, with a mane along its back. Later analysis suggests that this too corresponds closely with the known anatomy of the oarfish once its more fragile features have been lost. Taken together, these observations form a pattern that bridges narrative and biology. The same physical form appears in historical accounts, in cultural memory, and in modern identification, each layer adding clarity to the last. The transformation from living animal to legend does not require invention, only distance and time. In that space, the oarfish becomes something else, not through change in its nature, but through the way it is seen, remembered, and retold across generations. Along the western edge of Japan, where villages have faced the open sea for generations, knowledge was once carried not in instruments, but in memory, in patterns, observed slowly, and passed forward without written certainty. In these communities, the ocean was not only a source of food, but a presence to be read, its surface and its life offering subtle indications of change. Among these signs, one figure held a particular place, a long silver form known as Ryugu no Tsukai, a name that translates to messenger from the palace beneath the sea, a realm believed to belong to a dragon king who governed forces far beyond the horizon. The story does not treat the creature as an accident or a stray. Its appearance is described as deliberate, a movement upward with purpose rather than error. When it arrives at the boundary between deep water and shore, it is understood not as a creature out of place, but as one carrying information that cannot be spoken directly. The message is never described in detail, only an outcome, a change approaching, something large enough to alter the rhythm of the coast and the lives that depend on it. This belief is not recent. References appear in records preserved over centuries, woven into the practices of fishing communities along the Sea of Japan. These communities relied on observation as a primary form of understanding. The behavior of animals, the timing of tides, the arrangement of clouds across the sky. Each element contributed to a system of interpretation that existed long before mechanical measurement. Patterns were noted across generations, and those patterns formed a language that guided decisions when no other guidance was available. Within that language, the oarfish held a distinct role. Its rarity gave it weight, and its form made it unmistakable. When it appeared, it did not blend into the background of daily life. It stood apart, and that separation allowed it to be noticed and remembered. Over time, these moments were connected, not through formal analysis, but through repetition, each occurrence reinforcing the association between the animal and events that followed. Historical accounts suggest that unusual activity among marine species has preceded significant disruptions along the coast. Before the Great Earthquake in the early 20th century, reports describe changes in the behavior of fish and other sea life, movements that did not align with normal patterns. These observations were recorded in local narratives, not as data, but as experience, shared and preserved within the community. When the earthquake struck, causing widespread destruction and loss of life, those earlier signs were recalled and linked to what had occurred. As the 20th century progressed, advances in science introduced new ways of understanding the Earth. Instruments replaced observation in many contexts, and older forms of knowledge were gradually set aside. The legend of the oarfish shifted into the category of folklore, something acknowledged as part of cultural history but no longer considered a practical source of information. It remained in stories and traditions, but its role as a warning faded from everyday thought. Yet the memory did not disappear entirely. It remained present in language, in the continued use of the name, and in the quiet recognition that some patterns had once been noticed for a reason. When the ocean delivered another of these long silver forms to the shore, even in a modern setting, the older meaning could still be recalled, if only briefly. In this way, the legend persists not as a fixed explanation, but as a framework built from observation, shaped by time, and carried forward through continuity. It reflects an attempt to interpret a connection between the unseen movements of the earth and the visible changes at the surface, using the tools that were available at the time. The oarfish, in this context, becomes less a symbol and more a point of contact between two worlds, one hidden below and one lived upon above, linked through moments that are rare but remembered. In the early weeks of that year, the shoreline along the Sea of Japan began to receive a series of quiet arrivals, each one similar in form, each one separated by days that seemed ordinary at first. Along the coasts of Ishikawa and Toyama, long silver bodies appeared where they were not expected, carried in by tides that offered no clear explanation. These were not isolated events. Over the span of several weeks, the number grew, approaching 20 individual strandings, far exceeding the usual pattern in which one or two might be recorded across an entire year. Fishermen, local residents, and officials encountered them one by one, each discovery noted and discussed. The animals lay along the sand or drifted near the edge of the water, their forms unmistakable even to those who had never seen one before. Photographs circulated through regional media, accompanied by brief reports that described the unusual frequency of the sightings. The tone of these reports remained measured, yet beneath the surface, there was a quiet recognition that this sequence did not align with expectation. Within those same reports, the older name began to reappear. Ryugu no Tsukai was mentioned again, not as a certainty, but as a remembered idea that had not fully disappeared. The connection between these strandings and the deeper movements of the earth was not presented as fact, yet it lingered in the background of the coverage, carried forward through repetition and shared awareness. The modern framework of explanation existed alongside this older narrative, neither replacing the other entirely. As winter shifted toward early spring, the sequence continued without interruption. Each new appearance added to a growing sense of pattern, though no formal conclusion was drawn at the time. The coastline remained outwardly unchanged, the routines of daily life continuing as they always had, even as these rare events accumulated quietly along its edge. Then, on a day in March, the underlying structure of the region changed in a single moment. At a time marked precisely in the afternoon, the seafloor shifted with a force that extended far beyond the coastline. The earthquake that followed reached a magnitude of 9, the largest ever recorded in Japan, releasing energy that had been building over a long and silent interval. The movement propagated through the surrounding water, displacing it on a scale that reshaped the surface. The waves that formed traveled outward with increasing height, reaching coastal areas with a force that could not be contained. In some locations, the water rose to heights exceeding 40 meters, overtaking barriers and structures with equal ease. The impact extended across towns and cities, altering the landscape and leaving behind a record of loss that would be measured in thousands. More than 15,000 people were confirmed to have died, and many more remained unaccounted for in the immediate aftermath. In the days and weeks that followed, attention returned to the earlier strandings. Images and reports that had once seemed incidental were revisited, now framed within a larger context. The sequence of events, once viewed as unusual but isolated, began to take on a different significance when placed alongside what had occurred. Media outlets beyond the region began to report on the pattern, drawing connections that had not been widely considered before. Marine biologists and researchers were asked to address the possibility of a relationship between the two. The response, consistent across institutions, remained careful and precise. There was no established mechanism linking the presence of these animals at the surface to the timing of seismic activity. At the same time, the absence of a clear explanation did not allow for a simple dismissal. The available data was limited, and the phenomenon itself was rare. In this moment, the boundary between observation and interpretation became more visible. A pattern had been recorded, but its meaning remained uncertain. The events of that year did not resolve the question. Instead, they expanded it, carrying it beyond regional memory and into a wider field of study, where it would continue to be examined with the tools available and with an awareness shaped by both science and the persistence of older knowledge. In the years that followed, attention began to shift from scattered observation towards something more deliberate, an effort to gather what had been seen across decades and arrange it into a form that could be examined without the weight of memory alone. At Tokai University, a research group led by Yoshiaki Orihara set out to approach the question with structure, drawing together records that had previously existed in isolation. The aim was not to confirm a belief or dismiss it, but to place each reported appearance within a broader timeline and observe whether any consistent relationship could be traced. They began by assembling a data set that extended back nearly a century, collecting documented instances of deep-sea fish appearances, including oarfish and closely related species. The total reached 336 events, each one tied to a location and a date, each one representing a moment when something from depth had crossed into the visible world. These records were then placed alongside another set of data, 221 earthquakes of magnitude 6 or greater, occurring within the same general regions over the same span of time. The method was straightforward in its design. For each recorded appearance, The researchers examined whether a seismic event followed within a window of 30 days and whether it occurred within a defined geographic radius. The intention was to identify patterns that might not be visible in individual cases, to see whether clusters formed when the data was viewed collectively rather than as isolated incidents. As the comparison unfolded, the results settled into a form that resisted simple interpretation. Out of all the pairings examined, only a single instance met the criteria for what could be considered a statistically plausible correlation. In that case, the timing and location aligned closely enough to suggest a potential connection, but beyond it, the data did not support a consistent relationship. The majority of appearances occurred without any corresponding seismic event, and many earthquakes took place without any recorded deep-sea fish activity preceding them. Orihara's own conclusion reflected this balance. The analysis did not provide evidence strong enough to confirm the idea that these animals serve as reliable indicators of impending earthquakes. At the same time, it did not offer a definitive explanation that would fully separate the two phenomena. A second observation accompanied the findings, a reminder that the absence of clear evidence does not equate to the absence of an underlying mechanism. The dataset, while extensive in effort, remained limited in scope when measured against the rarity of the events it attempted to compare. This limitation forms the central difficulty. Both large earthquakes and oarfish strandings occur infrequently, and their occurrences are unevenly distributed across time and space. To establish a statistically meaningful relationship between two rare events requires a volume of data that may not be achievable within the span of recorded history. Even when patterns appear in small clusters, they can dissolve when viewed against a larger background, leaving behind only the suggestion of connection rather than confirmation. A separate study approached the same question with a similar framework, examining whether the long-held belief could be supported through available records. Its conclusions aligned closely with the first, identifying minimal correlation while acknowledging that the methods themselves were constrained by incomplete data and the inherent variability of the phenomena being studied. Within this careful structure, the question remains suspended between possibility and uncertainty. The data neither validates the legend nor replaces it with a complete alternative. Instead, it outlines the boundaries of current understanding, showing where observation has reached its limits and where further insight would require a depth of information that has not yet been gathered. Beneath the measured language of collected data, a different kind of explanation begins to take shape, one that does not rely on coincidence but on sensitivity, on the possibility that certain forms of life are attuned to changes that unfold long before they reach the surface. Among the proposed ideas, one stands apart for its consistency with known physical processes, suggesting that the oarfish may be responding to movements within the earth itself, not at the moment of rupture, but in the quieter period that precedes it. Along active fault systems, the buildup to a major earthquake is not a single event, but a sequence of gradual shifts. Tectonic plates press against one another, accumulating strain that is released in small adjustments, micro-movements that alter the surrounding rock. As this pressure increases, subtle changes occur. Tiny displacements, faint emissions of gas, and the generation of weak electromagnetic fields within the fractured material. These signals do not remain confined to the seafloor. They move upward through the layers above, carried through water in forms that are difficult to detect with conventional instruments. Within this context, the position of the oarfish becomes significant. It occupies a region close enough to the source of these signals that they would arrive with minimal distortion and in water that remains largely undisturbed. The stillness of that environment allows even faint variations in pressure to persist without being masked by currents or surface activity. In such conditions, small changes can remain coherent over distance, forming patterns that might be sensed by organisms adapted to that depth. A statement from Kiyoshi Watatsumi, associated with the organization ePISCO, reflects this perspective, noting that fish living near the seafloor may be more sensitive to fault movements than those nearer the surface. This sensitivity is thought to arise from the way certain species interact with their surroundings, relying on systems that extend beyond sight or sound as they are commonly understood. The oarfish possesses one such system, known as the lateral line, a continuous network of sensory cells that runs along the length of its body. These cells respond to changes in pressure and vibration within the water, allowing the animal to perceive movement at a distance. While all fish share this capability to some extent, the scale of the oarfish introduces a different dimension. Its body extends through a larger vertical range than most species, placing its sensory surface across multiple layers of the water column at once. In this configuration, the oarfish becomes a kind of elongated receiver, capable of detecting variations that pass upward from below. Infrasonic vibrations, too low in frequency to be perceived through ordinary hearing, may travel through the water as part of the pre-seismic activity. Electromagnetic fluctuations generated by stress within certain rock formations may also propagate into the surrounding environment. These signals, though weak, could interact with the biological systems of an animal that is both large and finely tuned to its medium. If such signals are detected, the response would not be intentional communication, but a reaction shaped by physiology. Disturbances within the body could lead to disorientation or stress, prompting movement away from the source. In the context of the oarfish, this movement may take the form of ascent, a gradual shift upward that brings the animal closer to the surface. What appears from above as a sudden arrival may in fact be the final stage of a longer process, driven by conditions that began far below. This interpretation does not assign purpose to the event beyond survival. The oarfish does not signal or warn in any conscious sense. It responds to changes in its environment using the mechanisms available to it, and in doing so, it becomes visible at moments when the deeper layers of the ocean are undergoing subtle transformation. The hypothesis remains unconfirmed, yet it aligns with known principles of physics and biology, leaving open the possibility that these rare appearances are reflections of processes that are otherwise difficult to observe. Across different landscapes and centuries, there are moments when animals move in ways that do not align with their usual patterns, subtle shifts that pass almost unnoticed until they are placed beside what follows. These movements are not confined to one species or one environment. They appear in burrows, along shorelines, within wetlands, and in enclosed spaces, each instance shaped by the conditions of its setting, yet sharing a quiet consistency. One of the earliest recorded accounts comes from an ancient coastal city where observers noted that small animals began to leave in unusual numbers. Mice, weasels, snakes, and even insects were seen moving away from their usual habitats in the days before the ground itself changed. The record, preserved in writing, does not offer an explanation, only a sequence: departure, followed by destruction. The city later lost beneath water after a powerful seismic event and the wave that followed it. Centuries later, in a different region, another pattern unfolded. In a city in northeastern China, snakes emerged from hibernation long before the season would normally allow it. Their appearance in the cold suggested a disturbance that extended beyond temperature alone. Local authorities, observing these changes along with other signs, chose to act. An evacuation was ordered, and when the earthquake struck, many lives were spared. The decision did not rest solely on animal behavior, but that behavior formed part of the larger picture that informed the response. In a more recent setting, a scientific team monitoring amphibians observed a similar departure. Toads that had gathered at a breeding site began to leave several days before a seismic event occurred nearby. The site remained largely empty until the sequence of aftershocks had passed, after which the animals returned. The timing of their movement, recorded with precision, added another instance to a growing collection of observations that suggested a connection between environmental change and animal response. Even in controlled environments, where external variables are reduced, comparable reactions have been noted. At a zoological park in a major city, various species displayed signs of agitation shortly before a moderate earthquake. Apes altered their behavior, birds moved in unusual patterns, and reptiles showed signs of restlessness. These changes occurred minutes before the event, within a window too narrow for most instruments to provide meaningful warning, yet sufficient for living systems to respond. Taken together, these accounts suggest that certain animals detect aspects of the environment that remain outside the range of typical human perception. Species that live in close contact with the ground or within water appear particularly responsive, their sensory systems attuned to subtle variations in pressure, chemistry, or electromagnetic conditions. The signals themselves are believed to originate from the processes that precede a fault rupture, shifts in groundwater composition, the release of gases such as radon, and fluctuations in electromagnetic fields generated by stress within the Earth's crust. These changes can occur over varying timescales, from days to moments, and may propagate through soil and water in ways that are uneven and difficult to predict. For an organism whose survival depends on detecting faint disturbances, even a small deviation from normal conditions can prompt movement. The response is not uniform across species, nor is it consistent in every instance, which makes it difficult to translate into a reliable system of prediction. Despite the number of observations, this phenomenon has not been formally integrated into earthquake early warning frameworks. The primary challenge lies in variability. Animal behavior is influenced by many factors, and distinguishing a signal related to seismic activity from other environmental changes requires a level of consistency that has not yet been achieved. Additionally, the mechanisms involved remain only partially understood, limiting the ability to model or anticipate responses with confidence. Within this broader pattern, the oarfish occupies a distinct position. Its habitat places it closer to the source of many of these pre-seismic signals, and its physical structure allows it to interact with its surroundings in a way that extends across depth. Its appearances are rare but highly visible, drawing attention in a manner that smaller or less conspicuous species do not. In this sense, it represents an amplified version of a more widespread phenomenon, a single example that brings into view a pattern that exists quietly across the natural world, deep within the structure of the Earth. Long before any visible motion reaches the surface, pressure gathers in silence, building along boundaries where rock meets resistance. In certain regions, this pressure does more than reshape the physical arrangement of the crust. It produces an effect that is less visible but equally real, a subtle conversion of mechanical force into electrical energy. This phenomenon, known as the piezoelectric effect, occurs when specific types of crystalline rock are compressed, generating small electrical charges as their internal structures shift under strain. Along many fault systems bordering the Pacific, the underlying geology includes quartz-rich formations, materials known to exhibit this property under sufficient stress. As tectonic forces accumulate over time, these rocks may begin to release faint electromagnetic signals, pulses that travel outward through both solid ground and the surrounding water. In controlled laboratory settings, this process has been observed and measured, confirming that stressed rock can indeed produce detectable electrical activity before fracturing. Translating this into a natural environment introduces complexity, yet the basic mechanism remains consistent. In the period leading up to a major seismic event, as pressure intensifies along a fault, the surrounding rock may emit a sequence of electromagnetic disturbances. These signals do not move in isolation. They propagate through the medium around them, passing into the water column above, where their strength diminishes but their presence may still persist as subtle fluctuations. Research conducted at Tokyo Gakugei University explored whether such signals could influence marine life, particularly species that inhabit deeper regions of the ocean. Some fish possess the ability to detect extremely weak electrical fields, a sensory capacity known as electroreception. This ability allows them to perceive changes in their environment that are not accessible through vision or mechanical sensation alone. It is a form of awareness that operates at a level of sensitivity difficult to replicate with instruments designed for broader measurements. The oarfish, however, presents a challenge within this framework. No living specimen has remained accessible long enough for direct testing, leaving its sensory capabilities in this regard uncertain. Yet, within its broader classification, there are indications that such sensitivity may exist. A closely related species, commonly referred to as the streamer fish, has been documented to generate mild electrical charges, suggesting that the family may possess an inherent relationship with electromagnetic phenomena, either in production, detection, or both. If the oarfish shares this capacity, the implications extend beyond simple perception. Electromagnetic pulses, rising from stressed rock, would not be experienced as distant signals, but as immediate disturbances within its environment. These fluctuations could interact with its sensory systems in a way that disrupts equilibrium, producing a response that is not deliberate but reflexive. The animal may begin to move, adjusting its position in an attempt to regain stability, and in doing so, it may rise through the water column. This movement would not be directed toward the surface with intent, but rather away from the source of disruption below. The ascent could be gradual at first, becoming more pronounced as the signals intensify or persist. By the time the oarfish reaches shallower depths, the original stimulus may no longer be present, yet the change in position has already occurred, placing it within a range where it becomes visible. Such a mechanism offers a potential explanation for the observed clustering of appearances in regions known for tectonic activity. Areas such as Japan and the Philippines sit along fault systems where the geological conditions necessary for piezoelectric effects are present. In contrast, earthquakes occurring in regions with different underlying structures may not produce the same electromagnetic signatures, and therefore would not elicit the same biological response. This interpretation remains within the realm of hypothesis, supported by known physical principles, yet limited by the absence of direct observation. It aligns with a pattern that has been noted but not fully understood, suggesting that the interaction between geology and biology may extend into domains that are only beginning to be explored. There is another pathway by which the hidden movements of the Earth may reach into the living world, not through vibration or electricity, but through chemistry, carried silently within the water itself. This pathway begins within the rock, in spaces too small to see, where trace elements accumulate over long periods without drawing attention. Among them is radon, a naturally occurring radioactive gas, present in minute quantities within both stone and groundwater, usually dispersed so widely that its presence remains negligible. As pressure builds along a fault, the structure of the rock begins to change in subtle ways. Microfractures form, spreading outward in patterns that mirror the growing strain. These fractures create new pathways through which gases can move, releasing radon from its confined spaces into the surrounding environment. This process has been observed repeatedly, not as a rare anomaly, but as a consistent feature in the lead-up to certain seismic events. Elevated concentrations of radon in groundwater have been recorded prior to earthquakes, forming one of the more stable indicators that something within the Earth is shifting. Once released, radon does not remain fixed in place. It dissolves into water, becoming part of the fluid system that moves through rock and sediment. From there, it rises gradually, carried upward through layers of groundwater and into the ocean above. The movement is not abrupt. It unfolds over time, forming plumes that expand and disperse as they ascend, altering the chemical composition of the water through which they pass. Within these deeper layers, organisms exist in conditions where even small changes can be significant. Chemical sensing plays a central role in how many species interpret their surroundings. Through gill structures and specialized receptors, fish detect variations in dissolved substances, responding to shifts that might indicate food, danger, or environmental change. In this context, an increase in radon concentration, though invisible, represents a measurable alteration in the medium itself. Laboratory studies have shown that elevated levels of this gas can induce physiological stress in fish, affecting respiration and internal balance. The response does not require high concentrations. Even moderate changes, sustained over time, may be sufficient to disrupt the equilibrium that deep-dwelling species depend on. For an organism already adapted to a narrow range of conditions, this disturbance can prompt movement, an attempt to leave the affected region in search of stability. If such a plume reaches the depth at which the oarfish resides, the effect may be experienced across its entire body. Its extended form increases the area over which these changes are detected, amplifying the signal in a way that smaller organisms might not experience as strongly. The response, again, would not be intentional, but reactive. A shift upward could begin as a gradual adjustment, continuing until the animal enters layers where the concentration has diminished. This interpretation aligns with the geographic pattern observed in recorded appearances. Regions where oarfish strandings have been documented frequently correspond to areas above active subduction zones, where one tectonic plate moves beneath another. These zones are associated with both significant seismic activity and the conditions that facilitate the release of radon into surrounding waters. Japan, the Philippines, and coastal areas along the eastern Pacific share this underlying structure, each positioned above boundaries where pressure accumulates over time. In contrast, earthquakes that occur in regions with different geological compositions may not produce the same chemical signals, or may do so in forms that dissipate before reaching higher layers of the ocean. This could account for the uneven distribution of reported strandings, with clusters forming in specific locations while remaining absent in others. Within this framework, the oarfish becomes part of a larger system in which geological processes influence biological responses through subtle changes in chemistry. The movement from depth to surface is not a signal in itself, but a consequence of conditions shifting below, carried upward through water in a form that living systems can perceive long before it reaches human awareness. Beneath certain stretches of ocean, the boundary between water and earth conceals a continuous motion that unfolds over spans of time far longer than any single observation. In these regions, one section of the planet's crust moves gradually beneath another, descending into the interior in a process that reshapes the seafloor from below. This is the defining structure of a subduction zone, a place where pressure accumulates steadily as two massive plates press together, their edges grinding and deforming as they converge. The movement is not smooth. It advances in increments so small they are almost imperceptible, yet each adjustment alters the stress within the surrounding rock. Over years and decades, this stress builds, held in place by friction until it exceeds the strength of the boundary. When that threshold is reached, the stored energy is released in a sudden shift, producing the earthquakes that reshape coastlines and send waves outward across the ocean. Along the Pacific margin of Japan, this process is marked by a deep trench that traces the edge of the continental shelf. The structure extends to depths approaching 9,000 meters, forming a narrow boundary where one plate descends beneath another. It was here that the movement responsible for the events of 2011 occurred, a release of energy that had been accumulating for an extended period beneath the surface that gave little indication of the scale of what was forming below. Farther south, a similar configuration defines the Philippine Trench, a feature that reaches beyond 10,000 meters in depth. The scale of this structure places it among the deepest regions of the ocean, yet its significance lies not only in its depth, but in the activity it sustains. The same forces of convergence and compression operate here, producing a continuous sequence of smaller adjustments punctuated by larger events. It is within this region that a notable cluster of oarfish appearances was recorded, aligned geographically with the boundary below. Across the Pacific, another subduction system runs along the western edge of North America, extending offshore from California through Oregon and into Washington. Known as the Cascadia Subduction Zone, it represents a similar interface between tectonic plates, one that has remained relatively quiet in recent history compared to others, yet is understood to be capable of significant movement. Geological analysis indicates that this region accumulates strain over long intervals, suggesting that a future release is not a matter of possibility, but of timing. Observations along this coastline have noted an increase in recorded oarfish strandings in recent years. Whether this reflects a change in underlying conditions or an improvement in documentation remains uncertain, yet the alignment between these appearances and the location of the subduction boundary invites further attention. The connection is not presented as direct causation, but as a spatial correspondence that mirrors patterns seen elsewhere. Even in the absence of major earthquakes, these zones are not static. The seafloor above them is shaped by constant microseismic activity, small shifts that occur as pressure redistributes along the boundary. Hydrothermal systems release heat and chemicals into the surrounding water, and slow fault movement, often referred to as creep, alters the structure of the crust over time without producing immediate rupture. Together, these processes create an environment that is in continuous motion, though much of that motion remains undetected at the surface. Within the water column above, conditions may appear stable, yet the influence of what lies beneath is always present. An organism occupying this region exists within a field of subtle variation, where changes in pressure, chemistry, and electromagnetic properties can emerge from below and propagate upward. The oarfish, positioned within this vertical range, moves through layers that are directly connected to these processes. In this sense, its environment is not simply defined by depth, but by proximity to ongoing geological activity. The signals generated within subduction zones do not always reach the surface in a form that can be easily measured, yet they may still be present in the layers where certain species reside. The challenge lies not in determining whether such signals exist, but in understanding how they are expressed and whether they can be interpreted through the movements of the organisms that encounter them. On a clear day near the southern coast of California, movement appeared where the water should have held only the usual rhythm of reef and current. Snorkelers drifting above a shallow stretch between La Jolla Cove and La Jolla shores noticed a long form suspended just below them, its presence out of scale with everything around it. The body did not dart or turn as other fish might. It remained extended, moving with a slow, continuous motion that seemed to follow a different set of rules, as though it carried its own measure of time into a place defined by light and surface activity. Encounters like this are exceptionally rare. The oarfish is not a species that approaches shallow water under ordinary conditions, and to see one alive in such an environment represents an event that most observers will never experience. The individual recorded on that day was an adult male, measuring approximately 3.73 meters in length, with a weight of around 33.7 kilograms. Its proportions remained consistent with what has been inferred from specimens found at the surface, yet here those proportions were intact, unaltered by the processes that usually follow arrival. It was transported to the Scripps Institution of Oceanography at the University of California, San Diego, where researchers were able to examine it while traces of its original condition remained. This opportunity, though brief, allowed for a level of observation rarely possible. The body retained its reflective surface, free of scales yet marked by a silvery layer that responded to light with subtle variation. Dark spots were visible along its length, and the red crest along its dorsal line remained defined, each filament distinct rather than collapsed or degraded. For scientists accustomed to working with specimens that have already begun to deteriorate, this presented a different kind of record. Internal structures could be studied with greater clarity, offering insights into musculature that confirmed how little mass is required to sustain its form. The composition of its skin revealed details about its fragility and resilience, while the arrangement of organs provided further context for how such a large body functions within a constrained environment. These observations did not resolve the broader questions surrounding the species, but they added precision to aspects that had previously relied on inference. Within a short interval following the sighting, a regional earthquake occurred in the same general area. The timing was noted, recorded alongside the location and the circumstances of the encounter. It entered the scientific literature as part of a sequence of events, neither emphasized nor dismissed, simply placed within the growing collection of instances where biological presence and geological activity appear in close proximity. Researchers studying the region have pointed to the underwater geography as a possible factor in the appearance itself. The coastline near La Jolla is bordered by submarine canyons that extend from deeper waters toward the shore, forming pathways through which water from greater depths can move closer to the surface. These channels create a connection between environments that are usually separated, allowing organisms from lower layers to approach areas where they would not typically be found. This configuration offers one explanation for why such encounters occur in this specific location. It does not require a change in the animal's behavior as much as a shift in the surrounding conditions, bringing the deeper environment closer to the surface rather than the organism moving entirely on its own. Yet even within this explanation, uncertainty remains. The presence of the oarfish in that moment could reflect a combination of factors, environmental, physiological, or otherwise, that are not fully understood. The specimen, though brief in its time above water, extended the range of what could be directly observed. It provided detail where there had been approximation, yet it did not answer the question of why it appeared when it did. That question remains within the same space as before, shaped by observation but not resolved by it, continuing to rest at the intersection of what can be seen and what remains hidden beneath. Seen from the shoreline, a stranding begins quietly, often without the drama that later surrounds it. A long shape lies near the edge of the water, partially lifted by the tide, its body tracing a line that does not belong to the usual forms found there. What appears at first as stillness is not yet the end of movement, but the last stage of a process that has already unfolded far below, guided by forces that change with depth. At the level where the oarfish normally exists, the weight of the ocean presses in from all sides with a steady, uniform intensity. Around 500 meters beneath the surface, pressure reaches approximately 50 times that experienced above, shaping the internal balance of the animal in ways that remain stable only within that environment. Every structure within its body, from tissue density to fluid distribution, is adapted to that constant force. When the fish begins to rise, whether carried by shifting currents or moving under its own altered state, the pressure surrounding it decreases continuously. This reduction is not gradual in its effect. As the external force lessens, gases dissolved within its tissues begin to expand, altering the internal equilibrium. Unlike species equipped with a swim bladder, the oarfish has no mechanism to regulate buoyancy through controlled gas exchange. Once the ascent begins, there is little capacity to slow or reverse it. As it moves into shallower layers, the physical character of the water changes. The stillness that once defined its environment gives way to motion. Currents intersect, waves introduce constant oscillation, and the body is subjected to forces it has not evolved to manage. The long, delicate structure that once moved with minimal resistance now encounters turbulence that places strain on tissues not built for such conditions. Movement becomes less controlled, and orientation begins to shift. By the time it reaches the upper layers, the effects are already advanced. Many individuals are still alive when first observed, their bodies moving in irregular patterns along the surface or in the shallows. These motions, often described as twisting or undulating, reflect a loss of coordination rather than deliberate behavior. The transition from depth to surface has disrupted systems that rely on stability, and the response unfolds in real time. Exposure to light introduces another change. The reflective surface of the oarfish, adapted to low illumination, reacts differently under direct sunlight. The silvery layer begins to dull as chemical reactions occur at the surface of the skin. Oxidation sets in, altering both color and texture within a short period. The red crest, once defined and upright, loses its structure as the supporting tissues weaken. It settles against the body, its color fading as the processes of breakdown begin. Time becomes a critical factor. In warmer surface waters, decomposition progresses rapidly. Within a span of days, the form of the animal begins to lose its clarity. Soft tissues degrade, structural features collapse, and the long, continuous shape becomes irregular. A specimen that once displayed a clear outline can become difficult to identify, its defining characteristics obscured by the changes that follow death. This transformation explains much of the confusion found in earlier accounts. Observers encountering such remains would have seen only fragments of the original structure, altered by both physical decay and environmental exposure. Without the context of a living example, the interpretation of these forms often shifted toward the unfamiliar, shaped by what could be seen rather than what had existed before. In this way, a stranding is not a single event but a sequence, beginning in depth and ending at the boundary between water and land. Each stage reflects a change in conditions, pressure, motion, light, and chemistry, all acting upon a body designed for a narrow range of stability. What arrives at the shore carries the imprint of that journey, though much of what defined it has already been lost along the way. There are moments in the recorded observations where the oarfish does something that does not align with the expectations built from other fish, something that seems to ignore the usual logic of movement in water. Instead of moving forward in a horizontal line, it turns its body upright, head angled toward the distant light above, tail extending downward into the darker layers below, holding itself in place as though the water were a column it could stand within. This posture has been captured more than once, through remotely operated systems and in rare footage taken in open ocean, including a recording from the Gulf of Mexico that offered one of the clearest views of the behavior. In each instance, the body remains nearly straight, its length forming a vertical line while the dorsal fin continues its subtle undulation. There is no sudden effort, no visible strain, only a steady suspension that contrasts with the more familiar patterns of marine movement. Among large fish, this orientation is unusual, to the point of near absence. Most species rely on forward motion to maintain stability, using fins and body shape to counteract the constant influence of gravity and buoyancy. The oarfish, however, appears capable of maintaining its position without the same reliance on horizontal propulsion, its structure allowing it to align with the water column in a way that other species do not attempt. Several explanations have been proposed, each addressing a different aspect of its possible function. One suggestion considers feeding, proposing that the fish may position itself to intercept small drifting organisms from below, allowing prey to move upward into its field rather than pursuing them directly. Another interpretation focuses on buoyancy, suggesting that without a swim bladder, the oarfish may use this orientation as a means of regulating its depth through subtle adjustments, balancing its position without expending significant energy. A third possibility extends beyond feeding or movement, focusing instead on perception. The body of the oarfish is lined with a lateral system, sensitive to pressure and vibration, a network that extends along its entire length. When the fish assumes a vertical posture, this system is no longer confined to a single horizontal layer. It spans multiple depths at once, effectively placing segments of its sensory surface in different parts of the surrounding environment simultaneously. In this configuration, the oarfish becomes something more than a passive observer of its immediate surroundings. It interacts with gradients, changes that occur across depth rather than within a single plane. Variations in pressure, shifts in water movement, and other disturbances that travel upward or downward can be detected along different points of its body at the same time. This creates a form of awareness that integrates information across a vertical range rather than relying on a single level. If signals originating near the seafloor move upward through the water, whether as mechanical vibrations or electromagnetic fluctuations, a vertically oriented body would encounter them along its full length. The lower portion might detect the earliest trace, while the upper sections would register the signal moments later, creating a sequence that could be interpreted as direction and intensity. In contrast, a horizontally oriented fish would experience the same signal at a single depth without the comparative information that comes from vertical alignment. This arrangement does not require that the behavior evolved specifically in response to seismic activity. It may instead represent a broader adaptation to an environment where subtle changes carry important meaning. Detecting differences in pressure could indicate shifts in surrounding water masses, the presence of other organisms, or variations in conditions that influence survival. The vertical posture allows these differences to be sensed with greater resolution. Over time, such a structure becomes more than a method of movement. It becomes a way of interacting with a layered environment, where information is distributed across depth rather than concentrated in a single place. The oarfish, through its form and behavior, occupies that structure fully, aligning itself with the vertical dimension of the ocean in a way that transforms its entire body into a continuous field of perception, shaped not by intention, but by the conditions in which it exists. Looking back across the months before the seafloor shifted, the pattern does not begin or end with a single species. The long silver forms that drew attention were only one part of a wider movement, a series of small deviations that unfolded along the coast and just beyond it, each one subtle in isolation, yet together forming a shape that was not immediately recognized. Along the Sanriku coastline, fishing communities reported catches that did not match expectation. Nets brought in species that typically remain in deeper water, animals not usually seen near the surface or close to shore. The change was not dramatic enough to interrupt daily routines, but it was noted, discussed briefly, then set aside as part of the variability that accompanies life at sea. In the absence of a clear cause, these moments remained separate, unconnected. During the same period, strandings of dolphins and pilot whales were recorded in greater numbers than usual. These events occurred across different stretches of coastline, spaced in time yet similar in form. Each instance was documented locally, treated as an individual occurrence rather than as part of a sequence. There was no immediate framework in which to place them, no indication that they might be related to something beyond the immediate environment. Above the water, patterns shifted as well. Records from observers tracking migratory birds noted changes in movement along the Pacific coast. Routes appeared altered, timings slightly offset, behaviors that did not align perfectly with established expectations. These variations, like those below, were recorded as anomalies, details that might warrant attention but did not yet form a cohesive narrative. Sea turtles also appeared in greater numbers along certain stretches of shoreline, their presence extending beyond what would normally be expected for that time. These strandings, like the others, were documented individually, each one entering a record without being linked to the broader set of observations occurring across the region. At the time, none of these events were gathered into a single framework. There was no system in place to compile observations across species and locations in real time, no method for comparing patterns as they emerged. Each report remained within its own context, separated by discipline, geography, and the natural limits of communication. It was only after the earthquake that these pieces were brought together, when the coastline had already changed and the sequence of events was complete. The earlier records were revisited. The unusual catches, the strandings, the altered movements, each was placed alongside the others, forming a pattern that had not been visible as it was happening. In retrospect, the clustering became clear, not because the events themselves had changed, but because the perspective had shifted. This reveals a central difficulty in interpreting animal behavior as an indicator of deeper processes. A single observation carries little weight. It exists within the normal range of variation, indistinguishable from countless other occurrences that pass without consequence. Even several observations, if separated in time or species, may not suggest a connection. It is only when they are viewed together across a sufficient span that a pattern begins to emerge. In the case of those months, the presence of approximately 20 oarfish, combined with the simultaneous changes observed in other species, creates a configuration that appears more significant when seen as a whole. Yet this significance exists primarily in hindsight. At the moment when each event occurred, there was no clear signal, only individual deviations from expectation. For science, the challenge lies in bridging this gap between observation and recognition. Detecting such patterns in real time would require a system capable of gathering and integrating data across multiple species and environments, identifying correlations as they form rather than after they have passed. Until such a system exists, the interpretation of these events remains dependent on retrospective analysis, where meaning is assembled after the fact rather than perceived as it unfolds. Prediction, in this context, is not simply the act of noticing that the Earth will move, but of determining when, where, and how that movement will unfold. The distinction between detection and prediction becomes important here. Instruments placed across the planet can record the exact moment when a fault begins to slip, translating that motion into signals that travel faster than the shaking itself. These systems provide seconds of warning, sometimes enough to alter immediate outcomes, yet they do not reach back in time to anticipate the event before it begins. The deeper challenge lies in the nature of the process itself. Faults do not behave in a linear or easily predictable way. Stress accumulates gradually, influenced by countless variables within the surrounding rock, and the release of that stress can occur under conditions that appear nearly identical to those that produced no event at all. The system operates within a framework that is sensitive to initial conditions, where small differences at the beginning can lead to entirely different results later. This sensitivity limits the ability to forecast with precision, even when large amounts of data are available. Over the years, researchers have identified signals that sometimes precede major earthquakes. Changes in groundwater chemistry have been measured, shifts in the shape of the land have been recorded, and variations in electromagnetic fields have been observed. Each of these indicators provides a glimpse into the processes unfolding beneath the surface, yet none of them appear consistently before every event. In some cases, multiple signals emerge together, while in others, a large earthquake occurs without any detectable precursor. Historical examples illustrate this variability. In one instance, authorities responded to a combination of observed changes and ordered an evacuation before a significant earthquake occurred. The decision reduced the number of casualties, demonstrating that under certain conditions, early action based on available information can be effective. In another case, within the same country, and under a similar scientific framework, an earthquake struck without warning, resulting in a far greater loss of life. The difference between these outcomes reflects the unpredictability inherent in the system rather than a lack of effort or observation. The difficulty arises from the fact that the variables controlling these events are not fully understood. The depth of the fault, the composition of the surrounding rock, the distribution of stress, and the presence of fluids all interact in ways that are complex and often hidden from direct measurement. Even when instruments detect changes, interpreting those changes in a way that leads to reliable prediction remains an open problem. Within this context, the behavior of animals occupies a boundary between observation and uncertainty. On one hand, it suggests that living systems may respond to aspects of the environment that are not yet fully captured by instruments. Their sensory capabilities allow them to detect subtle variations in pressure, chemistry, or electromagnetic conditions, potentially providing an early indication of change. On the other hand, these responses are influenced by many factors, and distinguishing a signal related to seismic activity from other environmental influences is not straightforward. This places animal behavior at the edge of what can be used as a predictive tool. It offers clues that may point toward processes occurring below, but those clues lack the consistency required for integration into formal systems. A pattern that appears meaningful in one instance may not repeat in another, and without repetition, it cannot be relied upon as a basis for action. As a result, the search for reliable earthquake prediction continues within a space defined by partial understanding. Each piece of evidence adds to the overall picture, yet the picture itself remains incomplete. The oarfish, along with other species that respond to changes in their environment, becomes part of this broader effort, not as a solution, but as one of many elements that reflect the complexity of a system still being studied. The pattern does not belong to a single cause. When the record is widened beyond seismic events, other moments begin to appear, instances where the same long form reaches the shoreline under conditions shaped by entirely different forces. Each occurrence carries its own context, yet the outcome remains similar: an animal from depth arriving at the edge of land, its presence marked by the same quiet disruption of expectation. After major storms, particularly those that move across the western Pacific, there have been repeated accounts of strandings along the coasts of Japan. These storms do more than disturb the surface. They extend their influence downward, altering circulation patterns that reach into deeper layers. Water that would normally remain stable begins to shift. Currents that are usually weak become more pronounced, and boundaries between layers are temporarily disrupted. In such conditions, organisms adapted to a narrow range of motion may be carried upward, not by choice, but by the changing structure of the water around them. Elsewhere, beneath the ocean itself, volcanic activity introduces another form of disturbance. When an undersea eruption occurs, it releases not only heat, but also a complex mixture of chemicals into the surrounding environment. Hydrothermal systems can change temperature gradients rapidly, altering the composition of the water in ways that propagate outward from the source. For species that rely on stable conditions, these shifts represent a sudden departure from equilibrium. Strandings have been documented following such events, suggesting that the effects of these changes can extend into the layers where the oarfish resides. Gradual changes also play a role. Over longer timescales, shifts in ocean temperature influence the movement of water across entire regions. As climate patterns evolve, currents adjust, sometimes subtly, sometimes more noticeably, altering the pathways through which energy and matter flow. Researchers have proposed that these changes may affect the mesopelagic zone, modifying the distribution of temperature and density in ways that influence where certain species can remain. In this framework, an increase in surface appearances may reflect not a sudden event, but a slow reconfiguration of the environment itself. Periodic climate phenomena contribute further variation. During phases associated with temperature anomalies, such as those linked to large-scale oceanic oscillations, the structure of the ocean can change across vast distances. These events have been associated with increases in strandings of multiple deep-dwelling species, including the oarfish. The connection is not always direct, yet the timing suggests that broader shifts in ocean conditions can influence the likelihood of these encounters. As more of these instances are considered together, the interpretation becomes less singular. The appearance of the oarfish at the surface cannot be assigned to one mechanism alone. Instead, it reflects a range of influences, each capable of producing a similar outcome through different pathways. A disturbance in pressure, a change in chemistry, an alteration in current, all can lead to movement that brings the animal into view. This multiplicity complicates the effort to associate strandings with a specific type of event. If the same visible result can arise from several distinct causes, then the presence of the oarfish becomes a broader signal, one that indicates a change has occurred, but not necessarily what kind. The distinction between different sources of disturbance becomes difficult to resolve when the observable endpoint remains consistent. Within scientific interpretation, this leads to a position that balances possibility with restraint. The connection between strandings and seismic activity remains part of the discussion, supported by certain observations, yet limited by inconsistency. At the same time, other mechanisms provide equally plausible explanations for similar events, each grounded in known processes within the ocean. What emerges is a view in which the oarfish is not tied to a single narrative, but exists within a network of environmental influences. Its movement toward the surface reflects a response to change, though the nature of that change may vary from one instance to another. The pattern remains, but its meaning shifts depending on the conditions that produce it, leaving the interpretation open to multiple paths that converge at the same visible moment. Records of this animal do not begin in laboratories, but in moments that unfold far from any instrument, along stretches of shoreline where observation depends entirely on who happens to be present. A fisherman pulling a net at dawn, a passerby walking the edge of the tide, a small group pausing at something unfamiliar in the sand. These are the points at which knowledge first forms, fragile and easily lost if no one chooses to carry it further. For much of recorded history, these encounters rarely traveled beyond the immediate scene. A large, ribboned body found on a remote coast might be noted in passing, remembered for a season, then gradually absorbed into local memory without ever entering any formal archive. Without photographs, without rapid communication, and without established reporting channels, most of these appearances simply disappeared from the global record. What remained was a scattered collection of documented cases, shaped less by how often the animal appeared and more by how often someone with access to scientific networks happened to witness it. This imbalance has left a deep gap in understanding. The dataset available to researchers reflects only a narrow slice of reality, limited to events that intersected with institutions capable of recording them. When studies compile sightings across decades, the numbers appear precise, yet they represent only the visible portion of a much larger pattern. The absence of records does not indicate absence of events, only the absence of documentation, a silence created not by the ocean, but by the boundaries of human observation. In recent years, that boundary has shifted. The spread of personal recording devices and global communication networks has altered the way these encounters are captured. An appearance that once might have passed unnoticed beyond a single village can now be photographed, shared, and circulated across continents within hours. The image becomes a form of data, carrying location, time, and visual detail, often before any formal investigation begins. This transformation has begun to fill in parts of the record that were previously inaccessible. With this change comes a new challenge. As documentation increases, it becomes difficult to distinguish between a true rise in occurrences and an increase in visibility. A pattern that appears to intensify may reflect improved reporting rather than a shift in the underlying behavior of the species. Researchers must now interpret a data set that is expanding unevenly, shaped by differences in connectivity, population density, and cultural attention. Regions with higher access to communication tools contribute more observations, while remote areas remain underrepresented, continuing the imbalance in a different form. Efforts are underway to address this complexity through coordinated data collection. Scientists are beginning to incorporate publicly shared observations into structured databases, aligning them with environmental and seismic records in an attempt to identify broader patterns. Each entry, whether originating from a formal expedition or a chance encounter, is treated as a piece of a larger system, one that may reveal relationships not visible within isolated datasets. The process requires careful filtering, validation, and contextualization, transforming informal reports into usable scientific information. Within this evolving framework, the role of attention becomes central. The stories that once circulated as local knowledge have drawn wider interest, prompting more people to recognize and document what they see. In this way, narrative has influenced observation, and observation in turn begins to reshape the narrative. The boundary between folklore and data becomes less rigid, not because they merge, but because each influences how the other is collected and interpreted. The result is a slowly expanding map of occurrences, still incomplete, yet increasingly detailed. Each new record adds depth to a pattern that was once fragmented, offering glimpses of continuity where there was previously only scattered evidence. The process remains ongoing, shaped by both human behavior and the hidden movements of the ocean, with understanding emerging gradually from the accumulation of moments that, for a long time, passed unrecorded. Far below the range of routine observation, there is a vast region of ocean that exists almost entirely outside continuous measurement, a space where processes unfold without interruption, yet leave only faint traces at the surface. It is within this quiet expanse that the limits of modern monitoring become most apparent, not because the environment is inaccessible in principle, but because sustained presence within it has only recently begun to take shape. Across the global ocean, instruments drift, anchor, and listen, forming a network designed primarily for events that have already occurred. Seismic arrays register vibrations as they pass, hydrophones capture distant echoes moving through water, and satellite systems observe changes at the surface with remarkable precision. These tools have refined the ability to detect earthquakes within moments of their release, yet they remain oriented toward confirmation rather than anticipation. The signals that precede such events, subtle and often transient, pass through layers of water that are only sparsely observed. Within the depth range where this animal moves, coverage becomes especially thin. Monitoring systems are distributed unevenly, shaped by logistical constraints, funding priorities, and the difficulty of maintaining equipment under persistent pressure and low temperature. Only a small fraction of this zone is continuously observed with biological sensors, and even within that fraction, data streams are often intermittent. The result is a landscape of observation marked by gaps, where long periods of silence separate brief intervals of recorded activity. The challenge is not only one of placement, but of endurance. Instruments designed for these depths must withstand conditions that slowly degrade materials and disrupt electronics. Power supply becomes a limiting factor, as continuous operation requires energy sources capable of lasting months or years without maintenance. Communication presents another barrier. Since transmitting information through dense water over long distances remains complex and resource-intensive. Each of these factors shapes the design of monitoring systems, often favoring short deployments or specialized missions over continuous presence. In recent years, advances in engineering have begun to extend the reach of these systems. More durable materials, improved energy storage, and more efficient data transmission methods have made longer deployments possible. Autonomous platforms can now descend, record, and return with stored data, while tethered arrays maintain a more stable connection to surface networks. These developments suggest the possibility of sustained observation within regions that were previously visited only briefly. With this growing capability comes the idea of integrating multiple forms of sensing into a single coordinated system. Acoustic detectors can register shifts in pressure waves, electromagnetic sensors can monitor subtle changes in the surrounding field, and chemical probes can detect variations in dissolved substances moving through the water. Visual instruments, operating in low light, can capture movement and behavior that would otherwise remain unseen. When combined, these tools create a layered perspective, each element contributing to a more complete picture of conditions at depth. If such a system were extended across key regions, particularly those above active geological boundaries, it could begin to capture the sequence of changes that unfold before larger events. Patterns that are currently inferred from scattered observations might emerge more clearly when recorded continuously. The absence of consistent evidence linking certain phenomena may reflect not a lack of connection, but a lack of sustained measurement in the environment where that connection would first appear. The present state of knowledge is shaped by this limitation. Observations arrive as isolated points, separated by time and distance, leaving large intervals unaccounted for. Without continuous data, it becomes difficult to determine whether these points represent rare coincidences or fragments of a broader pattern. Each recorded event stands alone, connected to others only through interpretation rather than direct observation. As monitoring extends deeper and remains in place longer, the nature of these connections may begin to change. What is now uncertain may gradually take on clearer structure, not through a single discovery, but through the steady accumulation of aligned observations. The ocean at these depths has always been active, always transmitting signals shaped by the movements of the planet itself. The difference lies in whether those signals are being recorded and whether they can be followed over time rather than glimpsed in passing. For now, the largest obstacle remains simple in form, a matter of presence rather than theory. The environment in question has not been watched continuously, and so its patterns remain partially hidden. As the reach of observation expands, the possibility of understanding expands with it, carried forward by instruments that remain where human presence cannot, listening to processes that unfold beyond immediate view. In the dim layers where light thins into a muted haze, life gathers in forms that seem shaped more by pressure and darkness than by any familiar pattern from the surface. Here, the long ribboned body moves among other inhabitants that share the same quiet conditions, each adapted in ways that feel both precise and improbable, as though the environment itself has guided their design over long spans of time. Among these companions drifts the giant squid, known to science as Architeuthis dux, a presence rarely seen yet widely inferred from traces left behind. It occupies similar depths, moving through water that rarely stirs, its limbs extending outward in slow, deliberate motion. Encounters with this animal are as fleeting as they are incomplete, and in certain moments, its appearance nearer the surface has been noted alongside broader disturbances, though the record remains sparse and difficult to interpret with certainty. Nearby, the frilled shark, Chlamydosalacus anguineus, moves with a different rhythm, its elongated form carrying features that have remained largely unchanged across immense stretches of geological time. Its body suggests continuity rather than change, a lineage that has persisted through shifting oceans and climates. On rare occasions, individuals have been observed in shallower water, often in states that suggest disruption rather than intention, their presence marking a departure from the stable depths they typically inhabit. Other forms rely on light not from above, but from within. The deep-sea dragonfish produces a faint red glow, a wavelength that travels only a short distance before dissolving into darkness. This selective illumination allows it to move unseen by most other creatures, revealing its surroundings without revealing itself. The light pulses softly, not as a constant beam, but as a controlled emission shaped by the needs of the moment. Suspended in the same environment, the barrel-eye fish carries a structure unlike any other, a transparent dome filled with fluid that houses its upward-facing eyes. These eyes can rotate within the enclosure, shifting orientation to track movement above while the body remains still. The arrangement allows it to observe without repositioning, conserving energy in a place where motion is measured and deliberate. The anglerfish completes this quiet assembly, extending a slender filament from its head, tipped with a bioluminescent lure that glows intermittently. The light does not flood the surrounding water, but gathers close, drawing attention inward rather than outward. Each pulse becomes a signal, a small point of focus in an environment where visibility is limited and distances are defined more by sensing than by sight. All of these animals exist within the same pressure regime, the same gradual gradients of temperature and chemical composition that define this depth. They are subject to the same subtle variations that move upward from the seafloor, whether those variations arise from geological shifts, chemical releases, or changes in the surrounding water. If signals precede larger events, they would pass through this shared space, touching each organism in ways that may not be immediately visible. Yet, their responses do not appear identical. The oarfish, with its extended body and distinctive orientation, occupies a different relationship to this environment. Its form stretches through a greater vertical range, its sensory systems distributed along a length that intersects multiple layers at once. Where other creatures remain within narrower bands, it moves across gradients, experiencing transitions that others encounter only partially. This difference may shape how each species responds to disturbance. Some remain below, their reactions contained within the depths where they reside. Others shift slightly, altering position without approaching the surface. The oarfish, by contrast, may traverse these layers more directly, its movement carrying it upward into regions where its presence becomes visible. In this shared world, the patterns of behavior are not uniform, but they are connected by the conditions that surround them. Each organism reflects a different way of existing within the same environment, responding to the same forces through structures and systems that have evolved along separate paths. The result is a community defined not by similarity, but by variation, all shaped by the same unseen currents that move through the deep. Long before instruments traced the motion of plates or sensors, listened for vibrations beneath the seafloor, there existed a different kind of understanding. One built not from measurement, but from repetition, carried quietly through generations, who lived in constant proximity to the water. Within that continuity of attention, certain patterns began to gather meaning, not as isolated events, but as sequences that returned often enough to be remembered. In those accounts, the deep was not described as empty or distant, but as structured and inhabited, a place where unseen forces moved with intention. The idea of Ryugu-jo, an undersea palace from which a greater presence governed tides, storms, and the shifting of the earth itself, emerged from this perspective. It was not a literal map of the ocean floor, but a way of describing a relationship between what lay below and what unfolded above, a language shaped by observation rather than instrumentation. Within that framework, the long silver body that occasionally rose into view was understood as a messenger, not because it brought information in a direct sense, but because its appearance coincided with moments when the world was about to change. The connection did not require explanation through mechanism. It was enough that the sequence repeated, that the presence of this animal preceded disruption often enough to become part of shared knowledge. From a modern perspective, stripped of symbolic language, the core of that observation remains intact. There exists a linkage between conditions in the deep ocean and events that reach the surface with sudden force. The pathways through which those conditions travel, whether through shifts in pressure, chemistry, or energy, are now studied with increasing precision. Yet the recognition that such a connection exists was established long before those pathways were named. The communities that first recorded these patterns did so through sustained attention over time spans that extended beyond individual lifetimes. Knowledge was accumulated gradually, refined through repetition, and preserved through story. Without formal records, the accuracy of these observations depended on consistency across generations, a form of continuity that allowed patterns to persist even as individual details faded. In this way, a series of encounters could be recognized as part of something larger, not because each event was fully understood, but because together they formed a recognizable sequence. Modern scientific methods approach the same question from a different direction, assembling data sets, applying statistical analysis, and searching for correlations that can be tested and replicated. This approach requires completeness, precision, and controlled conditions, all of which are difficult to achieve in environments that remain only partially observed. As a result, patterns that may be visible through long-term human experience can remain difficult to confirm within formal frameworks, not because they are absent, but because the available data is fragmented. The legend does not suggest that the animal causes the events that follow. Instead, it places the animal within a chain of awareness, a participant in a system that responds to changes before they reach the surface. This distinction aligns more closely with current hypotheses than it might first appear. The possibility that certain organisms detect shifts in their environment earlier than human instruments remains under investigation, not as a certainty, but as a question that persists alongside more established models. What emerges from this comparison is not a validation of myth as explanation, but an acknowledgement of its observational core. The language differs, the symbols differ, yet both perspectives point toward a shared recognition that the deep ocean is not isolated from the processes that shape the surface. It is part of a continuous system, one in which changes propagate upward, sometimes gradually, sometimes with sudden intensity. In this sense, the legend preserves an early attempt to describe a relationship that remains only partially understood. It frames the appearance of the animal not as an anomaly, but as a signal within a broader pattern, one that connects distant layers of the planet through pathways that are still being mapped. Across distant coastlines, separated by language, geography, and time, similar stories began to take shape, each rooted in encounters that seemed too unusual to remain isolated. These accounts did not travel between cultures in any coordinated way, yet they settled into forms that echo one another with a quiet consistency, suggesting that what was seen along one shore was not entirely different from what was seen along another. In the colder waters of the north, sailors spoke of long, gleaming shapes moving just beneath the surface, their bodies catching what little light filtered through the sky above. Descriptions of these creatures often included a trailing crest or mane, a detail that recurred across generations of seafaring tradition. Over time, these encounters were absorbed into the broader imagery of sea serpents, forming part of a narrative that blended observation with interpretation. The creature known as the lindworm emerged from this context, a form that carried the memory of something elongated, reflective, and difficult to fully perceive in motion. Far to the south, along the coasts of Aotearoa, oral traditions preserved accounts of large beings rising from deep water before moments of disruption along the shore. These stories were not framed as isolated curiosities, but as part of a pattern linking the ocean's depths to events that unfolded above. The details varied with the teller, yet the central idea remained that certain appearances preceded change, and that these appearances were significant enough to be remembered and passed forward. In the Mediterranean, where trade routes and coastal settlements fostered extensive written records, similar descriptions appear in texts that document unusual marine events. Ancient observers noted disturbances among sea life before episodes of geological upheaval, recording the presence of unfamiliar forms near the surface. Philosophers and naturalists attempted to categorize these observations within the frameworks available to them, sometimes attributing them to known species, sometimes leaving them unresolved. Within these writings, the outlines of elongated marine creatures appear again, linked not only to the sea itself, but to events that affected the land. Roman accounts, written in the context of a landscape shaped by volcanic activity, describe sightings of large serpentine forms near the coastline in periods leading up to eruptions. These descriptions do not always provide clear identification, yet they share structural similarities with accounts from other regions. The creatures are often described as pale or silver, their bodies extended, their movements unfamiliar when compared to the marine life more commonly observed in those waters. What becomes apparent through these overlapping narratives is not a single unified description, but a pattern of recurring features that persist despite cultural differences. Length, reflective surfaces, and a crest or mane appear repeatedly, along with the association between the appearance of these creatures and moments of environmental disturbance. The repetition does not confirm the identity of the animal in every case, yet it suggests that similar encounters occurred often enough to shape enduring traditions. The lack of direct contact between many of these cultures strengthens the significance of this convergence. Without shared communication, the emergence of comparable descriptions points toward a common source rooted in observation rather than exchange. Each account reflects the interpretation of a local environment, filtered through cultural frameworks, yet grounded in encounters that share recognizable elements. In the absence of consistent scientific documentation across historical periods, these narratives serve as a form of indirect record. They preserve details that might otherwise have been lost, capturing glimpses of events that occurred beyond the reach of systematic study. While the language differs from modern scientific description, The persistence of certain features across these accounts provides a thread of continuity that extends through time. Seen together, these traditions form a distributed archive, one that spans regions and centuries, linking distant observers through a shared experience of encountering something that moved between the depths and the surface. The similarities do not resolve every uncertainty, but they establish a context in which those uncertainties can be examined, anchored by the recognition that the phenomenon they describe was neither singular nor confined to one place. There are moments in scientific work when a single specimen carries more weight than years of scattered observation, not because it answers every question, but because it arrives intact enough to reveal details that have long remained hidden. The recent examination of a living individual, briefly held within controlled study, offered such a moment, allowing researchers to move beyond inference and into direct observation of structures that had previously been obscured by damage and decay. Within that brief window, attention turned inward, toward the arrangement of tissues and systems that govern how this animal experiences its environment. The internal architecture revealed patterns of organization that had not been clearly visible in specimens recovered after death. Along the length of its body, the sensory network, known as the lateral line, appeared more intricate than earlier studies had suggested, with a distribution that hinted at heightened sensitivity across extended distances. This system, embedded beneath the surface, forms a continuous interface between the animal and the surrounding water, registering subtle shifts that move through it. These findings align with a broader understanding that has been developing through genetic study. Analysis of its lineage places this species within the order Lampriformes, a group that traces back through vast spans of geological time. This placement situates the animal among forms that have persisted with relatively little structural change, maintaining characteristics that have remained stable across cycles of environmental transformation. Through periods marked by shifting climates, reorganized continents, and repeated disturbances in the structure of the planet, this lineage has continued to occupy the same general range of depths. Such continuity suggests that the strategies supporting its survival are not recent developments, but have been shaped gradually in response to long-standing conditions. In environments where tectonic activity is a constant presence, even if imperceptible on short timescales, organisms are exposed to recurring variations in pressure, chemistry, and energy. Over extended periods, those individuals capable of responding effectively to these variations would be more likely to persist, passing on traits that support that responsiveness. From this perspective, the possibility that certain behaviors are linked to underlying environmental signals becomes part of a broader evolutionary framework. If conditions preceding larger events create detectable changes within the water column, then organisms equipped to sense those changes may adjust their position in response. Movement away from areas of instability, even if it results in entering unfamiliar regions, could provide a temporary advantage if it reduces exposure to more severe conditions below. The ascent of this animal, when it occurs, may be viewed through this lens as a response shaped by accumulated selection rather than by coincidence alone. Its elongated form, its distribution of sensory structures, and its presence within a zone that intersects gradients of pressure and chemical composition all contribute to how it interacts with its environment. These features do not indicate a deliberate signaling mechanism, but they do suggest a capacity to register and react to changes that may not be apparent to other species in the same space. At the same time, the interpretation of these responses remains constrained by the limits of available data. A single, well-preserved specimen provides insight into structure, but behavior unfolds across contexts that are difficult to replicate or observe directly. Genetic analysis offers a timeline, but it does not specify the precise mechanisms through which environmental cues are translated into movement. Each layer of understanding adds detail, yet leaves space for further refinement. What emerges is a picture that is both clearer and still incomplete, where new observations align with existing hypotheses without fully resolving them. The animal's persistence across long spans of time, its anatomical features, and its occasional movement into shallower waters all suggest a relationship with its environment that is more complex than surface encounters alone might indicate. Within that complexity lies the possibility that its behavior reflects patterns shaped over durations far longer than any single record, patterns that continue to unfold beneath the surface in ways that are only beginning to be traced. There are stretches of knowledge where the outline of a subject becomes clearer even as its interior remains largely uncharted, a form that can be described in broad terms yet resists precise definition when examined more closely. This animal occupies that space, known in silhouette, yet still surrounded by uncertainties that persist despite years of observation and study. Time itself remains one of the most elusive dimensions. There is no reliable method for determining how long an individual lives, no structure within its body that records the passage of years in a way that can be read with confidence. Without this measure, it becomes difficult to place the animal within a temporal framework, to understand how its life unfolds from beginning to end, or how its experiences accumulate across its existence. Equally uncertain is the question of reproduction. No direct observation has captured the moment at which new individuals enter the world, nor the conditions under which that process occurs. The locations, depths, and environmental cues that guide this cycle remain unrecorded. Without this knowledge, the continuity of the species is understood only in the most general sense, inferred from presence rather than observed through process. Population size, a fundamental parameter for understanding any species, remains beyond precise estimation. The scattered nature of sightings, combined with the inaccessibility of the depths it inhabits, prevents the formation of a reliable count. What is known consists of fragments, individual encounters separated by distance and time, each one offering confirmation of existence without contributing to a comprehensive measure of abundance. Movement patterns introduce another layer of uncertainty. It is not clear whether individuals maintain consistent depth ranges or move fluidly through different layers of the water column over time. The paths they follow, the distances they travel, and the factors that influence these movements are largely inferred rather than directly observed. Without continuous tracking, these patterns remain suggestions rather than established behaviors. The question of interaction with others of its kind remains unresolved. Encounters are almost always solitary, leading to the assumption that the species does not form groups, yet absence of evidence does not confirm absence of social structure. Communication, if it occurs, may take forms that are subtle or transient, leaving no trace that can be easily detected by human observers. Certain physical features, striking in appearance, remain functionally ambiguous. The long dorsal crest, extending along much of the body, presents possibilities that range from display to sensory function, yet no single explanation has been confirmed. Its role may shift depending on context, or it may serve purposes that are not yet understood within existing frameworks. Observations of faint light emission in some individuals introduce further complexity. It is not known whether this property is consistent across the species or varies between individuals, nor is its purpose clearly defined. In an environment where light is scarce, even small variations in illumination can carry significance, yet the specific role of this phenomenon remains uncertain. Variation in size adds another dimension to this incomplete picture. Some individuals reach lengths far beyond those commonly observed, while others remain comparatively small. The factors that determine this variation, whether genetic, environmental, or a combination of both, have not been fully identified. Without understanding the drivers of growth, size becomes another characteristic that can be described but not explained. Finally, the broader question that has followed this animal through both folklore and science remains unresolved. The relationship between its appearances and events within the earth continues to resist simple classification. Whether these occurrences reflect a direct response to environmental signals, a pattern shaped by coincidence, or a mixture of influences remains open to interpretation. Taken together, these uncertainties form not a gap to be filled quickly, but a landscape that unfolds gradually as observation deepens. The scale of what remains unknown stands in contrast to the familiarity of the animal's image, a reminder that visibility does not equate to understanding. In the quiet spaces where data is still sparse, the outline persists, waiting for detail to emerge with time and attention. Far below the shifting brightness of the upper ocean, there exists a realm that has long been treated as distant from the rhythms of the surface, as though it were insulated from weather, from climate, from the restless movement of the planet itself. That assumption has begun to soften, not through a single discovery, but through a gradual accumulation of observations that suggest the depths are woven into the same system, responding in ways that are subtle, delayed, yet undeniably present. The waters where this animal drifts are part of a vast intermediate layer that holds an immense share of the ocean's living mass. In terms of sheer biomass, this region surpasses the fisheries that operate above it, yet it remains comparatively unobserved, its inhabitants rarely encountered except in fragments. The imbalance between what exists and what is studied reveals a gap not only in knowledge, but in attention, a quiet absence of sustained observation across one of the largest habitats on Earth. Within this layer, currents move with a patience that resists immediate perception. They transport heat absorbed from the atmosphere, carbon drawn from the air, and nutrients released from decaying life, carrying them across entire ocean basins over spans that extend beyond individual human lifetimes. These movements form a slow circulation that connects distant regions, linking polar waters to equatorial zones, deep basins to continental shelves, creating a system that redistributes energy and matter across the planet. In recent decades, careful measurement has begun to reveal changes within this circulation. Temperature gradients are shifting, chemical balances are adjusting, and the stability that once defined these depths shows signs of gradual alteration. These changes do not unfold with the abruptness of a storm, but with a steady persistence, altering conditions in ways that accumulate over time. For organisms adapted to constancy, even slight variations can carry significance. The creatures that inhabit this environment evolved within a framework of remarkable stability. Pressure, temperature, and chemical composition remained within narrow bounds across long stretches of geological time, allowing specialized forms to develop, each finely tuned to the conditions of its niche. Such specialization brings efficiency, but it also introduces vulnerability when the surrounding environment begins to change. As the chemistry of the ocean shifts, dissolved gases fluctuate, and temperature layers adjust, the signals received by these organisms begin to differ from those that shaped their evolution. Sensory systems that once interpreted stable patterns now encounter variation, and the responses that follow may reflect not only immediate stimuli, but the strain of adaptation to conditions that no longer align with inherited expectations. In this context, the appearances of deep-dwelling species near the surface take on a broader significance. They are not isolated anomalies, but potential indicators of underlying transitions within the environment itself. When individuals ascend from their usual depths, the cause may lie in a combination of factors, each contributing to a gradual displacement from familiar conditions toward regions that, while still challenging, offer a different balance of pressures and influences. The possibility that such movements are becoming more frequent introduces a shift in perspective. Rather than viewing each event as an isolated curiosity, it becomes part of a pattern that reflects the evolving state of the ocean. The drivers of these changes may include alterations in current patterns, variations in temperature, and shifts in chemical composition, all interacting within a system that is both complex and interconnected. What emerges from this view is a recognition that the deep ocean is not separate from the processes that shape the surface world. It participates in them, absorbs their influence, and in turn affects the conditions above. The boundaries between layers are permeable, allowing energy, matter, and signals to pass between them, creating a continuous exchange that links distant regions and disparate environments. Within this interconnected system, the movements of a single species can serve as a subtle reflection of broader change. The patterns observed are not definitive answers, but indications that the environment itself is in motion, adjusting in ways that extend beyond immediate perception. The quiet ascent of an individual from the depths becomes part of a larger narrative, one that speaks not only of a species, but of an ocean that is gradually, persistently becoming something new. Imagine, for a moment, a signal that rises quietly from the depths, not as a sound or a flash, but as a pattern unfolding across days, subtle at first, then unmistakable when seen as a whole. It does not arrive through instruments anchored to the seafloor or satellites orbiting above, but through the movements of living bodies, each responding to something that has not yet reached the surface world in any measurable way. If such a signal exists, and if it can be recognized with clarity, it would redefine the boundary between observation and anticipation. The difference between seconds and days is not simply a matter of scale, but of possibility. In one case, systems react, alarms sound, and people move only as the event begins to unfold. In the other, there is time to prepare, to shift entire communities out of harm's path, to reposition resources, to reduce loss in ways that current methods cannot approach. The devastation that follows a major rupture often unfolds with a speed that compresses decision into instinct. Water rises, structures fail, and the window for response narrows to moments. A longer interval of awareness would change the nature of that moment entirely, expanding it into something more deliberate, more measured, allowing actions that are currently beyond reach. The scale of impact would shift not through prevention, but through preparation guided by earlier knowledge. Yet the path to such knowledge is not straightforward. A biological signal is not a switch that turns on with certainty. It emerges from patterns, from repeated occurrences that must be distinguished from coincidence. Individual events hold little meaning on their own. It is only when they cluster, when they align across time and place, that they begin to suggest a deeper connection. Recognizing that pattern in real time requires a level of attention that has rarely been applied to the deep ocean. The challenge lies in transforming scattered observations into a continuous record. Each sighting, each appearance, must be documented, verified, and placed within a broader context. This demands coordination across regions, across institutions, and across the boundary between professional research and public observation. It requires systems capable of integrating visual reports with environmental data, aligning biological signals with geological measurements in a way that allows patterns to emerge clearly. Such an effort extends beyond technology into the realm of interpretation. Even with continuous monitoring, the meaning of a pattern remains uncertain without sufficient history to support it. Rare events provide limited data, and the relationship between cause and effect may remain obscured by variability. The presence of multiple contributing factors, each capable of producing similar outcomes, complicates the process further, requiring careful distinction between overlapping influences. Despite these challenges, the potential significance of such a system remains difficult to ignore. The cost of establishing and maintaining a network capable of observing these patterns across the ocean is substantial, involving deep water sensors, communication infrastructure, and sustained analysis over long periods. It represents an investment not only in equipment, but in time, patience, and the willingness to pursue uncertain outcomes. Against this stands the scale of what is at stake. Events of great magnitude carry consequences that extend far beyond immediate impact, affecting economies, environments, and communities in ways that persist for years. The value of even a modest improvement in early awareness accumulates across these effects, offering reductions in loss that cannot be easily quantified. In this balance between cost and consequence, the question becomes less about certainty and more about possibility. The ocean holds processes that are only partially understood, and within those processes may exist signals that have yet to be fully recognized. The movements of a deep-dwelling species, once interpreted as isolated anomalies, begin to suggest a pattern that invites closer attention. If the legend reflects a real connection, even imperfectly understood, then it points toward a form of knowledge that lies at the intersection of biology and geology. It suggests that the living world may register changes that precede measurable events, offering a glimpse of what is forming beneath the surface before it emerges above. There is a quiet accumulation to everything that has unfolded, a shape that only becomes visible when each fragment is allowed to rest beside the others without urgency. The glimpses, the strandings, the scattered records across distant coasts, they begin to align into something that feels less like coincidence and more like a pattern observed from different angles across time. For much of human history, this animal existed at the edge of perception, appearing briefly and leaving behind forms that defied familiar categories. Its body, altered by exposure and time, became something else in the eyes of those who found it, a presence that did not fit within known boundaries. From these encounters, stories emerged, not as inventions, but as attempts to describe what had been seen when no language yet existed to explain it. Across distant shorelines, separated by oceans and centuries, similar descriptions took root: a long, pale form, a crest of color, a movement unlike other fish. These details persisted, carried forward through memory and retelling, forming a shared understanding that something rare and significant had entered the shallows. The interpretation varied, shaped by culture and belief, yet the observation itself remained consistent. In the present, the language has shifted, replaced by measurements, classifications, and hypotheses, yet the core uncertainty remains. The mechanisms proposed, grounded in physics and biology, offer pathways toward understanding, but none have yet resolved the question fully. Each explanation accounts for part of the pattern while leaving other aspects unresolved, as though the phenomenon itself extends beyond any single framework. The environment in which this creature lives is one where boundaries are not fixed, where the processes that shape the solid earth intersect with the fluid motion of the ocean. Pressure, chemistry, and energy move through this space in ways that connect the living and the geological, creating conditions that are both stable and dynamic over different scales of time. Within this setting, sensitivity to subtle change becomes a form of survival. The lineage to which this animal belongs has persisted through vast stretches of Earth's history, enduring shifts that have altered climates, coastlines, and ecosystems. Its continued presence suggests an ability to navigate conditions that have repeatedly transformed, adapting not through speed or strength, but through alignment with the signals embedded in its environment. These signals, often imperceptible at the surface, form the background against which its behavior unfolds. When such an organism leaves its usual depth, the movement reflects a response to conditions that have shifted beyond its capacity to remain. The cause of that shift may vary, arising from geological strain, chemical alteration, or changes in the broader circulation of the ocean. Each possibility points to a reality in which the deep is not isolated, but actively shaped by forces that extend across the planet. What emerges is not a confirmation of ancient interpretation, nor a dismissal of it, but a recognition that the observations themselves carried meaning, even if the mechanisms were not understood. The appearance of this animal was noted, remembered, and associated with events that followed, forming a connection that persisted because it was grounded in repeated experience. Modern study approaches the same pattern with different tools, seeking to isolate variables and establish causation. Yet the limitations of available data, combined with the rarity of the events, leave the conclusion open. The absence of certainty does not erase the pattern, but it does frame it within a space that invites continued attention rather than resolution. In this way, the story remains suspended between knowledge and observation, shaped by both what has been measured and what has been noticed. The deep ocean continues to hold processes that are only partially understood, and within those processes, signals may exist that have yet to be fully interpreted. The presence of this creature at the surface becomes one of those signals, a moment in which the boundary between depth and air is briefly crossed. It does not announce a cause, nor does it define an outcome, but it reflects a change that has already begun below, unfolding beyond immediate view. Along some distant shoreline, at an hour when the tide has only just begun to withdraw, a shape will appear again, drawn from depths that remain largely unseen. It will lie across wet sand or drift in the shallows, its form unfamiliar to those who encounter it, yet already recognized in a quiet, collective way. The moment will not remain isolated. Images will be captured, shared, carried across networks that span continents, transforming a local discovery into something observed by many within a single day. From there, the pattern that has been forming begins its quiet expansion. Coordinates are noted, time is recorded, the surrounding geography considered. Somewhere, researchers will add the event to a growing archive, placing it alongside others separated by years and oceans, yet linked by their rarity. The process is methodical, patient, and incomplete, each entry a small addition to a record that is still far from whole. Attention then shifts toward the structures beneath the ocean floor, toward boundaries that lie far below the reach of ordinary observation. Records of subtle shifts, tremors too faint to be felt, are examined. The passage of days is marked, then weeks, as the search for connection continues. Sometimes nothing follows, and the event remains an isolated point within the archive. At other times, movement occurs, and the record gains another layer of association. Through this ongoing accumulation, a form of understanding begins to take shape, though it remains tentative, always subject to revision. The data does not resolve into certainty, but it does not fade into randomness either. Instead, it occupies a space between, where patterns suggest meaning without fully revealing it, and where each new observation carries the potential to clarify or complicate what has come before. The animal at the center of these observations remains unchanged by this process. It does not alter its behavior in response to human attention, nor does it participate in the interpretation that follows its appearance. Its existence continues within a realm defined by pressure, temperature, and darkness, conditions that shape its movements in ways that are governed by immediate necessity rather than distant consequence. When it enters the shallows, the transition is not one of adaptation, but of displacement. The environment that sustains it no longer holds, and the forces that once supported its form begin to act against it. The interval between its emergence and its stillness is brief, leaving behind a form that invites examination even as it begins to change. What remains afterward is not only the physical trace, but the record created by those who observed it. This record becomes part of a larger effort, one that extends beyond individual events, seeking coherence across time and space. It is an effort defined by persistence, requiring repeated observation, careful comparison, and a willingness to accept that answers may emerge slowly, if at all. The ocean, in this context, is not a silent expanse but a system in constant motion, carrying signals that are distributed unevenly, sometimes visible, often concealed. These signals move through water, through rock, through the living organisms that inhabit both, forming a network of interactions that is only partially understood. Within this network, certain events rise to the surface, offering brief moments of visibility. Each appearance contributes to a broader narrative, one that is still being assembled. The meaning of that narrative is not fixed, and its interpretation evolves as new information is added. What remains consistent is the presence of the pattern itself, recurring with enough regularity to invite continued attention. In this way, the process continues, observation following observation, record following record, gradually extending the boundaries of what is known. The deep ocean remains vast, its processes unfolding beyond immediate reach, yet not entirely beyond perception. Signals emerge, are noticed, and are preserved, forming the basis for understanding that develops over time. What is being revealed is not a single answer, but a relationship, one that connects the unseen depths with the world above. The nature of that connection remains unresolved, but its presence is increasingly difficult to ignore, suggesting that the ocean has long been expressing changes that are only now beginning to be recognized.